Hello and welcome to this video. In this video we're going to do two practice questions. One of them will be looking at how we can solve for the forces acting on a particle when we have more than one charge in a system, and the second question is going to be looking at how we can calculate the potential at a position when we have more than one charge in a system. So let's start with the force question. Now we're going to say that we have similar to how we did in the gravitational fields. Let's say we have one charge here that is, I don't know, let's say plus 16q, and let's have a charge here that's plus 4q, okay? Now, if we then want to know, let's say these are a distance d apart, same as before. Let's say we want to know at what distance from the 4q charge will a positive test mass feel 0 newtons of force. Okay, so sorry, positive test charge now, isn't it? Positive test charge feel 0 newtons of force, which means we have to then say if a positive test charge was in here somewhere and it got too close to the 4q, it's going to get repelled from 4q, and then it's going to go over to 16q and it's going to get repelled from there as well. Get repelled from both sides. We're saying at what point along the line in between them would it be repelled from the 16q charge by the same amount that it's repelled from the 4q charge, such that its overall force is 0. In order to do that, we have to say that, let's imagine we have some positive test charge that just has a charge of plus little q. Then we can equate the forces, so we can say that the force from the 16q is going to be 4 pi epsilon naught times 16q times the charge of the small test mass, because that's what we're focusing the force on, divided by, and we're going to say that this distance here is d minus x, because we want to know the distance from the 4q now, so we define that to be x. So this is over d minus x squared, and that must be equal to 1 over 4 pi epsilon naught 4q q over x squared. Now the first thing we can do is simplify this expression. We can cancel this whole factor of 1 over 4 pi epsilon naught. We can cancel both q's on both sides, and actually we could divide both sides by 4. So we could say that this is going to be 4 here, and this is just going to disappear to 1. From just that alone, we've now got it to 4 over d minus x squared is equal to 1 over x squared. And now we solve for x, and you'll notice we've got to the exact same expression that we got to in the gravitational force video. I then square root both sides, so I end up with this must be the same as 2 over d minus x is equal to 1 over x, and therefore I can then say that 2x is equal to d minus x. Therefore 3x must be equal to d, and that means that x must be equal to 1/3 of d. Okay, so I end up with, if I go 1/3 of the total distance between them away from the 4q charge, I end up feeling 0 force. Now you can do this for any charges. The trick with this though is they have to be like charges. It's not possible to do when they are not when they're oppositely charged, because if I put a positive test mass in here, it's going to be repelled from one side and attracted to the other side, so it's only ever going to go towards that one side. You won't find a position where the force is going to be 0 from in the middle. If we were to do that example, for if I scroll down a little bit, if I were to have a positive test charge here, or a positive charge here and a negative charge here, the positions where the force due to this negative charge will be the same as the force due to this positive charge, but in the opposite direction, it will be either over here somewhere or over here somewhere, not between the two, okay? So they will mostly get you to do this kind of question when you're looking at two like charges, okay? Now the second kind of question that we can have is looking at how do the potentials sum when I have a multi-bodied system. So let's now say instead of just having one charge, it's very rare to find one charge by itself. Let's say I have 4 charges, and let's say I put them in some sort of field that's set up so that they are equidistant from each other. And I have a charge of plus q from this one, I have a charge of plus q over here, I have a charge of plus q here, and I had a charge of plus q here. And these are 4 corners of a square. Okay, now what they say is they put all of these in a square that has a distance here of a meters between the two, and this is a square, so that means this is also a meters. Then at the very center of this, they put a point which we're going to call the point Z, and the question is asking you, what is the potential at point Z? What is the potential at Z? And so what we have to do, knowing that these potentials will just sum together because they're scalars, we just need to work out the potential from one of these things and then times it by 4. Since all of these things are positively charged, they will just add together with no subtractions. If you were to then have 2 positives and 2 negatives, for example, you might end up completely cancelling out the potential. But for this case, let's say that we have this potential at Z. The formula for potential we know is 1 over 4 pi epsilon naught q over r. Okay, so we know this formula. So now let's just focus on this one here. Okay, and I'm going to say I want to first find, I know what the charge is. This is a constant. I need to find the distance between this and this. Okay, now this is something you will be expected to be able to do. So let me talk you through how we would get to that. So this is the point Z, and this is the distance r. And what I'm going to say is I know that this is, if this is the center of this, it's exactly halfway along this distance, which means if I draw this triangle a little bit bigger, that means that this distance here is a over 2, relating to this distance here, is halfway along a, and this distance here is also a over 2 because it's halfway along the horizontal a, which means actually I have a right angle triangle where both of these are a over 2, and I just need to work out the hypotenuse. So what I do is I say r squared is going to be a over 2 all squared plus a over 2 all squared. So I end up with, this is going to be a squared over 4, this is going to be a squared over 4, so I end up with r squared is a squared over 4 times 2, so I end up with a cancellation here, so I can say r squared is actually a squared over 2, and then I can square root, and I can say that r is therefore a over the square root of 2. Okay, now I can keep this like this, but we usually rationalize it, so you can say that I'm going to times the top and bottom by root 2 just because it's much neater that way, I feel, and so I get root 2a over 2, and this is actually the distance that I feel like would probably be the best to use in this case. So I now know that the distance is root a over 2, so I can calculate my potential from the first charge. Okay, now the thing that's nice about the example that I've got here is that it is a square, so the distances from each of them will be equidistant. I don't have to calculate this for any others. I only have to calculate this once using Pythagoras theorem, and then as soon as I have that, I'm basically good for all of them. They will all have the same radius. So from the first charge, the potential that sums at point Z is going to be 1 over 4 pi epsilon naught q over root 2 times a divided by 2, but that 2 is going to come to the top, so I'm going to put that over here. So actually I can simplify that to just 1 over 2 pi epsilon naught by cancelling a 2 on top and bottom times q over root 2a. Okay, now this is just from the first charge here. I've still got 3 other contributions, so when I add these together, I could say that's the same as saying the total potential at z is just going to be 4 times the potential at 1. So I take 4 times 1 over 2 pi epsilon naught now, q over root 2 of a. And this leads me to then get 4 over 2 pi epsilon naught, q over root 2 of a. I can cancel a 2 on the top and bottom, and I end up with the potential at z is actually 2 over pi epsilon naught q over root 2a. Okay, now this is your general answer for this. And from here, you can apply this same method to any other potentials question. So you always just want to work out the potential due to one of them at a time and then add them all together at the end. Usually they're quite nice with these questions, and they tend to just make it, they'll have the same magnitude of charge, but they'll change the sign or something like that. But you'll just add them together, and the potentials will either be positive or negative depending on the charge that you have being positive or negative. Okay, so hopefully both of these questions make sense. As always, do more practice questions than just this video. Make up your own examples, have different charges on each corner, use different geometries, see if you can do this with a rectangle. You do it basically the same way, and then see if you can get to considerable answers that look okay. Thank you for watching.